on Monday, we went over gravitational field strength, and we discovered that gravitational field strength is numerically equal to, or the same as, okay, the gravitational acceleration at any given point. And obviously, just like the force of gravity, that is affected by mass. It is affected by distance. Okay? And then we discovered that it has this formula, which is derived basically by doing this, saying Fg equals Fg. Well, I mean, obviously, they're the same thing. They should be equal. Okay? But what we did was say m times g equals big G times mass 1 times mass 2 over r squared. Okay? And what we did is we discovered that what this says is the mass on this side, the small mass, ends up canceling with the small mass on that side, because all things, regardless of their mass, would fall at the same rate at any distance, or at the same distance, sorry, from the Earth's center. Okay? That's why we said during the satellite motion lesson that it doesn't matter whether you put a basketball, a garbage truck, or a giant space station at a certain point in orbit, they would all have to move at the same speed to maintain that orbit, because they all fall at the same rate at that distance. Right? So that's where this formula comes from. It's really just derived from the force of gravity. My warning to you that day was that you have to be mindful when a question is, or how a question is worded. If the question says, calculate the gravitational field strength, it wants this. If it says, calculate the force of gravity, or the mutual attractive force, or the force of attraction, it's looking for exactly what it says, a force. Right? Don't get the two confused. I told this to my afternoon class, and I forgot to tell it to you. On your unit exam, every year I put a question about gravitational field strength. And in that question, I write, calculate, and then I put in bold-faced, italicized, underlined font, the gravitational field strength, and then there's some other context after that. Okay? Inevitably, even after giving you this little lecture and warning you specifically about that question, 1/3 of you will still calculate this. I want to be wrong about this. But in more years of teaching than I care to tell you, I have not been. Even after giving this warning and telling you exactly what I'm going to do, okay, I still have between 25 and 30% of people do it that way. Okay? We need to understand that gravitational field strength is not a force. It's a rate of attraction. Okay? It's how many meters per second squared is it moving towards the other end? Okay? Or how many newtons per kilogram, or whatever. Okay? But it's not the same as force. Field strength is measured as a rate of acceleration. Force is measured as a force in newtons.
I was going to ask if that 1/3 was an actual number you recorded or something you just made up, but you kind of just answered that.
Yeah, no, yeah, seriously, when I go through the test, I just count how many times it happens, and yeah. So I would really like to have that number be less than 25%. Be awesome. Okay. I have confidence. It can be you. It can be. So what I would like you guys to do right now is I would like you to try these questions on gravity, specifically gravitational field strength. Okay? They ask, some of those things that we talked about, like the stuff with the Earth radii, okay, distance from the surfaces and from the center, okay, little tricks like that we just have to be kind of experienced with perceiving. All right, so I'm going to give you a little bit of time to work on those questions. Okay. So there's 3 of them there, and then we'll have a look at those, do a few more gravitational field strength questions, and then I'll do the unit exam review. Okay. Yeah. Okay, let's have a quick look at number 1 here. So on number 1, we have a satellite that's orbiting at a distance of 3 Earth radii above Earth's surface. That means its actual orbital radius is how many Earth radii? 4. Okay, so we got to do radius equals 4 times 6.37 times 10 to the 6. Okay, and that'll give us our actual Earth or actual orbital radius. Okay, so that's part A. How many Earth radii is it? Okay, and then the second part is what's the magnitude of the gravitational acceleration of the satellite? So we actually don't have to do any manipulation. Okay, we're just going to have g times the mass of the Earth divided by our radius once it's calculated squared. So we'll have 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 divided by 4 times 6.37 times 10 to the 6 squared. Okay, so when we punch all that in, we should get the answer that they have there, which is 0.611 meters per second squared. Okay, questions on any of the other ones? Happy to go over others if there's trouble with them. Everybody's good? 3, yeah. Okay, so highest satellites on Earth, orbit Earth at a distance of 6.6 Earth radii. So we'll just quickly get our actual orbital radius there. So we'll go 6 times 6.37. Was it above the surface? From the Earth's center. No, okay. E6. So there's our actual orbital radius.
6.6.
Oh, was it 6.6? What did I put in?
You just said.
I just put 6 in. That's a better number. Okay. So we've got, what would be the gravitational force? What are they asking for? They're asking for Fg. So again, that's me, and the textbook throwing in one of those things just to check, are you reading the question? Are you checking it carefully? Does it say field strength? Does it say force? Okay, so we got to be on the lookout for that. So force of gravity would be 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 70 kilograms divided by r squared, that number we had there a minute ago. So we'll have brackets. Okay, so 16 newtons is the gravitational force that object experiences. Okay, so just again, it's just wording, it's just stuff we got to watch out for, okay, and be alert for. All right, so what I would like you guys working on right now would be a couple of questions from the workbook. And you'll also note that I did put in the stream this morning the exam review package. Okay, so that is there for you to use as well. All right, so there are 9 gravitational field strength questions in the workbook, and so we'll have you work on a few of those here for right now. And then we'll move on to the exam review. So let's say, number 2, number 2, 3, 4, 8. Okay, let's have you guys try those 4 for right now, okay, and then we'll move on to the exam review. Okay, so 3 objects positioned in a straight line from left to right. They are 181, 70, and 405. there is no scale. I just drew it. Okay, so the 70 kilogram mass is 0.310 meters from the 181, and actually that's not too bad for scale, for the distance anyway, 0.460 meters from that one. What is the net gravitational force acting on the 181 kilogram object? All right, so there are two force of gravity calculations to do. Okay, we're going to call this 1, 2, and 3. So the force of gravity between 1 and 2 will be 6.67 times 10 to the minus 11 times 181 times 70 divided by 0.310 squared, and the force of gravity between 1 and 3. So that'll be 6.67 times 10 to the minus 11 times times 181 times 405 divided by 0.770, yeah? Is the radius there? And that'll have to be squared, right? So when we find those two numbers, we just add them together, and we've got the net gravitational force for that question. Okay, because we have to add those two distances together to get the center to center distance for the 181 and 405. Okay, so it's, the 181 is being pulled only to the right, and our vector, which we would have to include, would be to the right for whatever our newtons ended up being. 1.7 times 10 to the minus 5 newtons right or towards the other two masses or along the positive x-axis, anything that denotes a vector that's headed that way. Okay. All right, everybody's good with those? There's almost always one like that on the test. Because we're about to do the exam review, I just figured I'd mention. Okay, so let's look at our review here. Okay, so first thing we went over, okay, in this unit was uniform circular motion, but specifically we went over the principles of uniform circular motion. How does circular motion happen? Okay, what are the conditions that are necessary for it to occur and continue? Okay, things like that. So we need to understand that circular motion is the result of an object traveling at a constant speed, but constantly accelerating towards the center of a circle. Okay, so that was kind of the big thing. It has to have a constant centripetal acceleration caused by a centripetal force that is always pulling towards the center of the circle. So there'll be some multiple choice questions about the principles of uniform circular motion. Okay, so changing velocity, okay, constant speed but changing velocity. We talked about centripetal acceleration was v squared over r. We talked about Fc being mv squared over r equal to mass times acceleration centripetal. Okay, all of that kind of stuff. So, like I say, some multiple choice questions, kind of just checking your understanding. Not so much calculation to do with that. Okay. Then we talked about unbanked curves, which there'll definitely be some problem solving about, okay, in the written response, and there could be the odd multiple choice question about it. What keeps you in an unbanked curve is friction, and that's pretty important to remember if you're going to solve any problems related to it. So the centripetal force is equal to the force of friction because it is the force of friction that's providing it. Okay. And then we got mu mg equals mv squared over r, because obviously m times g is equal to the normal force, which is in that formula, mu times normal force. Okay, because it's not banked, normal force and gravity are equal. Okay. On that same day, we talked about banked curves, which work a little bit differently. A banked curve is essentially an inclined plane. You will not have to derive the banked curve formula, or tan of theta equals v squared over r times g, okay? But you do need to understand how to use it, okay, and what it's for. Right? So remember that in a banked curve, okay, as soon as we bank the surface, Now normal force pushes perpendicular, still pushes perpendicular to the surface, but now that force is angled off of vertical, which means the vertical component balances gravity and the horizontal component pushes towards the center of the circle, providing us with a centripetal force not reliant on friction. Okay? Now, in reality, do bank curves still rely on friction? They do, but they don't have to. Okay? And so, that's why they all have a yellow, generally a yellow speed sign. Okay? Because yellow means recommended. White means it's the law, it's the limit. Okay, yellow means it's recommended. So, yeah, you have to obviously base your speed on the conditions. Okay? Can you go faster than the recommended speed under ideal conditions? Yes. Not a lot faster. Okay, don't try and go twice as fast. Okay, but you can go a little faster because friction will be there, right? But if the conditions are poor, okay, that speed is safe, and it should be taken at that speed. All right, so that's obviously the purpose of bank curves. There's the odd multiple choice question about bank curves, okay, but mostly there's going to be some problems about bank curves, or one problem. Okay, and then we talked about, sorry, that was how we derived the formula, but you won't have to do that. That's your bank curve formula. Just make sure you remember that that's what it's for. And then we talked about artificial gravity, where if we have a spinning drum and we're on the inside of it, then we can simulate the force of gravity using our inertia. Our inertia pushes us against the inside of the drum, and the drum pushes back towards the center of the circle, making us feel like we actually have weight, and everything would behave as though we have weight, and you would not have atrophy of your bones and muscles, and it would all work really good. Okay, so remember that in an artificial gravity situation, we are wanting the centripetal force, which is provided by the normal force, to feel like we're at home. Okay, so we would want it to feel like it's mass times 9.81.
If you were in an artificial gravity thing and it was like spinning around, but you ran the opposite way fast enough, would you be weightless?
No.
Why?
Why? Because you're still pushing on it to do so. So even though you might be walking or even running opposite its direction of spin, you're still spinning with it. Right? Now, as soon as you lose contact with it, then things are different. And as you go towards the center of it, if you climb a ladder that goes towards the middle, you'll get lighter and lighter because your speed and your radius are decreasing. All right. Yeah, it's kind of the same thing. Yeah, if you like run on a train, so the train's moving forward, and if you run backwards, you don't necessarily run any faster. Right? Sure, the train is moving, but you were initially moving with it.
Right.
So when you run, even if you're running the opposite way, to someone standing and watching you, you would look like you were running like or staying put, but you're not.
Just doesn't inertia require like a magnitude and direction?
No,
Does it-
inertia is quantitatively measured by your mass. Right? It does have to do a bit with like you want to do a certain thing, but that's because of your mass. So yeah, like even in like if you're running forwards on a train and somebody's watching you from the side, you look different than if you're just standing in place, but it's relative. Yeah. It's a good question. So then we have vertical circular motion. Okay, in vertical circular motion, obviously this is the most important thing. Okay, that regardless of which of the three positions we talked about is being questioned, that rule applies. Okay, centripetal force is equal to the forces in minus the forces out. Okay, so we dealt with three positions. Okay, we dealt with the top on the outside, and okay, you've got normal force pushing up, you've got gravity pushing down, unless you're going fast enough that you lose contact with it, in which case you feel weightless. Okay, if you're on the top on the inside, you must achieve your minimum speed. Okay? If you do not, you will fall out. If you go faster than the minimum speed, then you will push on the track and normal force will be apparent. And it will be your apparent weight. I didn't do that on purpose, that was a happy accident. Okay, so you'll have that apparent weight. If you go just the minimum speed, how will you feel? Weightless, because you won't be pushing on the track and it won't be pushing on you. If you are at the bottom, you always feel heavier if you're moving. Okay? If you're just sitting there, obviously you feel normal, but as soon as you get moving, you will feel heavier because your inertia wants to leave the circle, which pushes on the track. Your weight pushes on the track has to push back even harder, okay? And as a result, you feel the heaviest at the bottom. Okay? Everybody with me on that one? Okay, and then we talked about universal gravitation after that. Okay, so there'll definitely be some vertical, or at least one sort of circular motion problem. Okay, then we talked about universal gravitation. Okay, remember, because this is something that comes up in the multiple choice, that force of gravity is a mutual attractive force between the objects. Okay, and obviously we calculate it by going big G, universal gravitational constant, multiplied by the two masses that are interacting and attracted to each other, okay, and then divide that by r squared. And that, remember, is the distance between their centers. And if you see any of those tricky terms like surface, height, or altitude, okay, then you know you're missing something. Okay, from there, okay, remember you could have a net, will have a net gravitational force question, possibly on the context of the Earth, Moon, and Sun. And you will need to be able to calculate the net force of gravity on one of the three. I think that's supposed to be my diagram of the Sun, the Earth, and the Moon. It's pretty crappy. Okay, then we talked about satellite motion. You can see here, height, altitude, surface. There's those three key words. Okay, they come up most often with gravitational field strength and satellites. FC equals big FG for all satellite motion. Okay, I know a few of you figured out that you could solve satellite motion with Kepler, and it was true for the one question. Okay, but you have to have exactly the right information to do it. Okay, and if you do and you know how, good on you, I'll give you full marks for doing it. Okay, but for most of us, we're going to go FC equals FG because that will always work. When we're doing that, if we're dealing with a planet orbiting the sun, what are some things we need to be aware of that we might get and have to convert?
Kilometers to meters.
Could get kilometers to meters or even astronomical units to meters. Remember, I actually forgot to go over this that day, but an astronomical unit is the exact distance between the center of the sun and the center of the earth, which is on your formula sheet. Okay, it is 1.50 times 10 to the 11 meters. So if it says 1 astronomical unit or 3 astronomical units, you are simply multiplying the Earth's orbital radius by that many. Okay, by however many astronomical units it was. Remember also in satellite motion that you may need to do this substitution thing that I demonstrated a bunch of times, okay, where we substitute in 2 pi r for v, which results in it being 4 pi squared r over t squared. Okay, that's going to happen occasionally, so just be ready for it. Okay, that's what I'm demonstrating right there. And then gravitational field strength. Okay, remember that you need to be ready for that term, to be watchful for that term on a question so that you solve it correctly. Okay, it's not big time marks on the exam, but you'd probably like to get as many as you can. Okay, we talked about Kepler, but I only have multiple choice questions about Kepler on the exam. Okay, so just make sure you go over what we talked about, basically his laws. Okay, so the law of elliptical orbits, the law of equal areas, and this is the law of periods. Okay, If you have those and you can recognize them, like, you know, you might get a question that says, which of the following would Kepler agree with? Okay, be looking for one of his three laws. Okay, that said, Cavendish is also important. Okay, he's the one who came up with that torsion balance thing. We watched the video of how that actually works in reality. You know, he's the one who came up with big G, so his experiment's pretty important. Could be a multiple choice item as well. All right, 15 multiple choice, 8 written. Hang on, that might be old. Hang on, that might be old. Let me double check here. I feel like I changed something that no longer applies.
Okay. No, it doesn't. It's on our math class.
Okay, there are 33 marks in the written. Sorry, I was thinking the whole test was 33. There's 33 marks in the written, 8 questions in the written. And there's 15 multiple choice for a total of 48 marks. This is by far the shortest test you will write for me. Okay, your last few have been 60, 58, 62 or something like that. Okay, so this is quite a bit shorter. Okay, so use your time effectively. You should have lots of it. I will still, of course, allow you to come in and start early or you guys, will be able to write into lunch hour, as we always do. Okay, period 3, you can always come in and start early, but hey, you are welcome to still do that, even though I don't think you're going to need it. All of the givens, all the same things that are on your formula sheet are on the front page of the test. So you're going to get acceleration due to gravity, gravitational constant, Earth, Moon distance, Earth, Sun distance, radius of the Earth, mass of the Earth, mass of the Moon, mass of the Sun. And you'll get all the formulas from kinematics to where we are currently, set up as kinematics, dynamics, energy, circular motion, and then a heading on gravitation. So all the formulas we have covered are there, including the Unbanked Curve formula. Okay, so things that are going to be in the multiple choice. Again, properties of circular motion, or principles of circular motion. Different types of curves, okay, the fundamentals of banked curves and unbanked curves. There's some stuff about vertical circles, again, the principles of vertical circular motion. Some universal gravitation, some satellite stuff, banked curves, principles of circular motion, Kepler, universal gravitation, principles of circular motion, gravitation. Okay, so lots of stuff about your understanding of the basic principles of circular motion. Okay, written response. Unbanked curve, banked curve, gravitational field strength. Now, I changed this and I forgot to boldface, italicize, and underline. So that's not boldfaced, italicized, and underlined, but what I will tell you is it asks you to calculate, or actually gives you your acceleration due to gravity. And then asks you to calculate something else. Forgot that I changed that question. I was so tired of it going badly that I changed it. Forgot all about it. Okay, so that one's different now. There'll be an experiment. See if we do better with it worded differently. Vertical circle. Satellites, gravitation, artificial gravity and satellites. Two satellite questions. Okay, questions from you guys? Anything you want me to go over or cover in a bit more detail? Ian? Okay, so all you need to know about Kepler is these three laws. Okay, the law of elliptical orbits, which say that everything orbits in an ellipse. Okay, the law of equal areas, which says that as the planet is going around, if I have an equal time interval, like let's say 30 days, the planet will sweep out the same area each time. So if this is the ellipse that the Earth orbits in, okay, over here on the wide part of the ellipse, okay, that area and this area over here, even though they look different, are equal, because this is 30 days and this is 30 days. Okay? But the amount it traverses in its orbit is different. That's, remember we talked about how the seasons are all different lengths? Okay? That's why. It's the elliptical nature of the Earth's orbit. Okay, and then the law of periods is that mathematical death blow to the terracentric model. Okay, that says that the period of, let's say, Earth squared divided by the radius of Earth's orbit cubed would equal the period for Jupiter squared divided by the radius of Jupiter's orbit cubed, or for Saturn, or for Uranus, or for Neptune. Oh, I put E's. Sorry, supposed to be J. Yeah, so any two bodies orbiting the same point, the same central point, will have the same Kepler constants. Okay, and again, it's just a matter of being able to recognize what things Kepler came up with in a multiple choice question. Right? I mean, you can use this in certain situations. In fact, one of the two satellite questions you could use it for if you knew how to use it. Okay? But there's no advantage or disadvantage to using it or not using it. Okay. What else? Artificial gravity? Okay, so with artificial gravity, you stand inside and you have very short legs and long arms. Okay, and you stand inside this drum and the drum spins. Spins, let's say, this way. Okay, because it spins, your inertia wants you to leave the circle. Okay, your mass wants to go in a straight line according to Newton's first law at a constant velocity. But the curve, the inside of the drum, prevents it and pushes you back towards the middle. Okay? That push back towards the middle is dependent on the radius of the circle and the speed at which the circle is moving. Okay? Which is why we can set it up and say the centripetal force is equal to the force of gravity. Okay? However I want them to feel, okay, is based on how big the circle is and how fast the circle is moving. The mass is irrelevant. Okay? We're basically using centripetal acceleration to simulate gravitational acceleration. Okay? And they all work essentially that way. Okay. What else? Okay. Well then, you have available to you in the stream the circular motion exam review. Okay, so if you click on that, okay, there's basically just some quick review of those concepts, some suggestions for you, okay, and then there's some practice problems, okay, for you to try. The answers are in bold, so some additional study material there, okay, that you are more than welcome to use. Yeah, if more questions come up before the end of class, let me know, and I'll be happy to answer them for you.